Hello and welcome to Data Science in Industry vlog. My daughter told me that this vlog is quite boring without unboxing a toy. That is why today I would like to unbox something, because definitely she was right. So today I have a box. As you see, I started the unboxing process. So let us see what is here. Surprise, surprise! Balloons! Okay, different colors, different shapes, and a pump. Yeah, her birthday is coming, so I will use this opportunity to unbox balloons and give you some analogy to the topic of today's video, to the optimization. So, what I can do with this toy, I can inflate the balloon, I can push the pump, and there we see the effect. I can push it 2 times and the effect is even bigger. So the balloon is getting bigger and bigger. I have also another type of a balloon. Let it go. I will take this one. So it's a different type of a balloon. Oh, this pump is not working here. Let's pretend that it works. So what I'm telling, why do I tell about this? Because this pump and this balloon is an energetic process, let's say industry process. So I know that when I push the pump, this is my decision to push the pump, I will see the result. Yeah? The result differs depending on how many times I will push the pump. So this is a predictive model, a digital twin, right? I can do the digital twin of this process. So great, I have a digital twin, but why do I need this? Suppose we have a factory, the factory that inflates the balloons. So it gets the balloons, different types of balloons, and inflates them. The optimization task is to maximize the income in this factory. So we have a limited resources, pumps. Our decision is to how many times I will press the pump and what type of a balloon I will associate it with the pump. Let's say there are 2 types of balloon. The cost of those 2 types of a balloon, I think, is different. Yeah, it differs. You can see different costs in here. So, with limited resources, how to maximize the profit from the production? How many times I have to push the pump in each balloon to get the proper shape within some limits and avoid kaboom effect. So I don't want to destroy the balloons, I want to inflate them. And what time of balloon associate with the pump, assuming I know the demand for different types of balloons. So this is an optimization task. As you can see, I need to have this digital twin, the predictive model, in my optimization task. And today I would like to tell you about different optimization algorithms that we were using in our projects that we made for industry, and how to combine this optimization algorithm with machine learning tasks, with machine learning models that are based on the data from the production, from the control systems, etc., etc. So I hope it will be interesting. There will be a bit of mathematics, but don't be afraid of this. This mathematics is your friend. Here I would rather give you the tutorial, I will give you the few examples of useful optimization algorithms without going deep into details, deep into theory. I will try to explain how they work, when to use them to solve particular problem that exists in industry, and how to combine them with predictive models, with data science, with machine learning. So I hope you enjoy, and I will split this topic into two videos, part 1 and part 2. In part 1, I will focus on the optimization algorithm that are using continuous variables, like what should be the set point for temperature or pressure, what should be the amount of heat produced in the particular heat source, what should be the flow associated with the compressors. Those are continuous decisions. And in the second part, I will talk about this optimization tasks where the discrete decision variables are used. So should I turn on or turn off this plant, or should I use this device or not? And then I will show you how to combine those two words, how to solve the task where you have discrete decisions and continuous variables. Plus, I hope I will be able to show you some code made in Julia to show you that you can actually translate those abstract tasks into code and solve the problem. So let's start with part 1. So why do we need those optimization methods? Why it is so important topic in the Industry 4.0 concept? In plants, in factories, we are dealing with nonlinear, multi-input and multi-output processes, and they are simply complicated. Dispatchers, operators, they are making their decision based on their knowledge, experience and intuition. They know about some relations between process inputs and process outputs, but they cannot cover all the interconnections between inputs and outputs. We are, as a human beings, we are used to think in the 3D world. We are making our decisions based on 3 most important parameters. So when the process has many inputs, like hundreds of inputs and tens of outputs, it's really hard to take into consideration all those relations when making a decision. Moreover, stability and process safety are the main priorities for the operators, for the dispatchers, for people who takes care of industrial processes. Usually they like to have the high margin, the high safety margin, stability margin. As a result of this, the plant or the factory usually operates away from the optimal operating point. By using mathematics, we can reduce the safety margin, but still, thanks to this mathematics, thanks for those methods, the process is safe and stable, and operate closer to the edge. And usually the optimal solution is on the edge. Moreover, even relatively small changes to the process parameters can essentially influence the income or the reduced costs. So, for instance, if we increase the efficiency of a power boiler in the power plant by 0.25%, only this value, we can save up to 200,000 euro per year in, let's say, the power unit which has 200 megawatts. So even small changes, we should fight for them because they result in the big savings. So let's see the simplest formulation of the optimization task. We will focus, at the beginning, we'll focus on the optimization of a function with one variable. Our goal is to minimize or maximize the function, and the x is the decision variable. We call it decision variable. So we can decide about the value of this variable. By solving this problem, we mean finding such a value of x for which the value of f is the lowest possible. And we call it the optimal solution. So that this is the optimal solution of this task. And by the way, if we say that something is optimal, it means it's the best. The favorite song of the optimal solution is Simply the Best by Tina Turner. So we cannot say that something is more or less optimal. It has no sense. Something is more the best or less the best? No. If we are maximizing the profit in optimal solution, that the profit is maximal. We cannot say that something is more or less maximal. Or if we are minimizing costs, in the optimal solution, the costs are minimal according to assumed objective function. So we cannot say that something is less or more minimal. It's minimal and that's it. So when we say it's optimal, we cannot say it's more or less optimal. It's optimal, so it's the best, assuming the objective function, that is the formulation of our optimization goals. Okay, so now we can see the example. The function looks like this. So how to find a solution? As you remember, many times I told you that gradients are our friends. They tell us where is the optimal solution. So if we calculate derivative of this function, this is the derivative, we have to check where it is equal to 0, and that the optimal solution is 2, because for 2 it's equal to 0, and moreover the second derivative is positive, so the solution here, this is the minimum, not the maximum, this is the minimum of this function. Yeah, it looks like this. So derivatives and second derivatives helps us. That is why we like to formulate our optimization tasks using equations for which we can calculate derivatives. Yeah, here is the shape of this function and the optimal solution for x equal 2. But of course, in reality, we have many constraints, like the physics, for instance, like our predictive models, like some technical constraints, that the flow cannot be higher than some value, the pressure has to be higher than some value, etc., etc. So there are inequalities, like keeping the temperature lower than 90 centigrade, and equalities. For example, if I increase the pressure by some value, the temperature will rise by some value, right? So to solve this task is to find such values of decision variables. In this case, x is a vector, so it consists of x1 variable, x2 variable, etc., etc., for which the objective function, the mathematical formulation of our goals, returns the lowest possible value, the minimum value, with respect to constraints, those equalities and inequalities. The optimization is usually about minimization. We're trying to minimize costs, we're trying to minimize fuel consumption, we try to minimize emissions of harmful gases. But sometimes the same task can be formulated as maximization of incomes, maximization of efficiency, and we can easily switch between those two forms, because the minimization of a function f is the same like maximization of a function minus f. Decision variables need to be included in constraints, otherwise it is not constrained optimization. So we are only interested in such constraints, like you remember the predictive models, the digital twins of those processes are constraints, in fact. So we are interested only in such constraints that have something to do with our decision variables and an objective function. Here you can see the example of the wrong formulation of the task. So we have to minimize the function x1 plus x2, but the constraints are for x3 and x4, so they have nothing to do with decision variables. One more example of a wrongly formulated task. Here we have to remember that the solution, the solution domain, or we call it the feasible region, determined by constraints, cannot be empty. It cannot be an empty set, because otherwise there is no solution of this task. Yeah? So we want to minimize the function x1 plus x2, but take a look on the constraints. On one hand, x1 needs to be lower than 5. On the other hand, x1 has to be higher than 6. So there is no solution. The task is wrongly formulated. And here is another example. So we need to, in this case, maximize the function x1 and x2, and we have constraints. x1 must be higher than 0, the same with x2. It also has to be higher or equal 0. So, the solution is somewhere in infinity. This is also a bad formulation. We have to limit our solution domain, limit our feasible region in order to find the finite optimal solution. Here you can see the example of the proper formulation of an optimization task. Here our goal is to maximize the function f, function of x1 and x2, which is x1 plus 3x2. Let it be that, x1 is the number of produced items of product A, and x2 is the number of produced items of product B. Or, to the analogy of the balloon factory, number of inflated balloons type A and number of inflated balloons type B. But maybe let's stick to the number of items of products. And first, the cost, the income for each item of product A is $1, so we skip this one here, and income from the single item of product B is $3. So by maximizing this function, we'll maximize our incomes, our profits. But there are some constraints, like x1 minus x2 is less than 0, so we have to produce more items of product B than product A, and some other constraints, like we cannot produce more items of product B than 6 because maybe we don't have enough subtracts, etc., etc. So we have a set of constraints, and we have to solve this linear programming problem. Linear programming because all the equations here and inequalities as well, equalities and inequalities are linear. Everything is linear. The simplest possible case. So how to find a solution? And now let's try to draw the lines where the objective function has the same value. Because this is the objective function, and this is the equation of a plane. So here we can see this plane. So everywhere this is x1 axis, x2 axis, and here you can see the plane Here on this line, the objective function has a value 1. So if we would like to maximize this function, it's obvious that we should go this direction. But of course, we have some constraints, like the fact that the number of items of product B so x2 has to be higher than x1. Yeah, so we have, if this is the equation, this is the line that represents these constraints, we have to be above this line, which is good because probably the optimal solution is somewhere there. On the other hand, there are other constraints as well, like this one. And we know we have to be lower than this line. Moreover, we have to be below this line and above, on the right side of this line. So here we have a feasible solution space, region. So the optimal solution is somewhere here. As we look at this, probably somewhere here. So this is the feasible region. And now we have to find a point at which the value of the objective function is the highest. Yeah, we have to maximize the function. For linear programming tasks, this point is located on the feasible region boundary, on the edge, on the constraint somewhere. So in order to find this point, in case of linear programming, linear problems, we are using the simplex method. It's a very efficient, very fast method that finds the optimal solution. It's here. This is the optimal solution because this is the, as you can see, this plane that represents the objective function. It has the highest value here. It cannot go further because of constraint. Here is the simplex algorithm. The idea behind it is to walk along the edges of the feasible region because, as we already know, the optimal solution is on the edge. On the next slides, we will discuss the gradient-based optimization methods. We started with the linear programming problem, and we will use it to show how the gradient-based methods are working. But of course, please remember that in case of linear problems, the simplex method is the one you should choose, not the gradient-based method. This is just for the illustration of the concept of the gradient-based methods. It will be very useful when we will have more complex nonlinear problems. So in gradient-based method, first of all, we have to select the point which is within the feasible region, inside the feasible region. In order to do so, we are usually solving additional task at the beginning. This is a simplified task where we're trying to minimize, this is also the optimization task, right? We're trying to minimize how much we are violating constraints, right? If we are not violating constraints, it means that we find the minimum, which is 0. It means that we are within the feasible region. It is done automatically by those methods. Then we need to we need to calculate derivatives against decision variables for x1 and for x2. We see that the derivative for x1 is 1 and for x2 is 3. So it shows us the direction, right? We need to increase x2 and x1, but we need to increase x2 3 times more than x1. So this is this arrow. somewhere there is an optimal solution. So we can treat it as in the same way as if you have a ball, small ball, and we are on the hill. We put the ball on the ground and it just starts to rolling down. The direction in which it's rolling, it's let's say it's decided by the gradient of this hill. So our ball is rolling this way, not down but up in this case, because we are maximizing the function. If we will minimize it, it will roll down. So now we can do the small step in this direction, right? So one step forward. Okay, great. We haven't reached the constraint, so we can do another step, right? And we should continue until we reach the boundary. If our ball hits the fence, the boundary, it will roll down, touching the fence, right? So now we will go up as high as possible without violating this constraint. So we will do such step. Here we cannot go any higher because of this constraint. So what we can do is we can still move higher but slower, because we have to touch this constraint. So we are going and going and going, and finally we are reaching this point. We cannot go any higher than this because of this particular constraint, this one and this one. So this is the optimal solution. The gradient tells us where to go, and constraints limits our movement. This is, I think, a simple explanation of those gradient-based methods. In case of nonlinear objective function, things are even more interesting. So this is the, let's say, efficiency map, efficiency characteristic of a device in a function of two parameters. It could be flow and the pressure difference, if this is a pump, or other parameters. It's some device. It's in fact a real device, a real compressor characteristic, but we will use it for some theoretical discussions right now. So the optimal solution is here. This is the maximal efficiency of this device. And there are some constraints. X1 has to be higher than this value and lower than this value. X2 has to be below those lines because of some technical restrictions. So we find this is our starting point, and we are doing one step forward in the direction of a gradient. Then our hill gently changes the shape. So the gradient, the new gradient is calculated here. We have to turn left a bit, then once again and once again. After every step, the new gradient is being calculated. And by following the gradient, we are reaching the optimal solution. Of course, we can have two small steps, and we will look for this optimal solution for a very long time, or our steps can be too high, and we can jump over the optimal solution and be somewhere here. So the size of this step is also important. It doesn't have to be constant. There are methods where the size of this step changes. Okay, and now let us change the constraints a bit. Now it looks like this. So the the point where the efficiency is maximal is here, but because of some constraints on some relations between the parameter x1 and x2 of this device, we cannot go here. And because of this, when we reach the boundary, the gradient will tell us that we should go somewhere there, but we will have to go through this, trying to go to this point pointed out by the gradient, but without violating these constraints. So we are touching these constraints and going up, I would say. So the optimal solution is somewhere here. Today, the peak of this hill, of this mountain is closed, so we have to do this picnic below the peak. All right, so in case of nonlinear programming, so the optimization task where the equations are nonlinear, gradient-based methods are suitable for convex problems. I will explain later on what is the convex problem. And of course, I'm talking about continuous decision variables right now, right? I will talk about discrete decision variables later on. So continuous decisions, it means that I search for the optimal parameters of, I don't know, temperature, pressure, flow, right? But I'm not deciding about if the device is turned on or turned off, or what is the mode of the compressor, serial or parallel, is it one stage or two stage compressor, etc., etc. So if we are forced to deal with nonlinear tasks, and this is reality is generally nonlinear, we should try to express it with quadratic function, because there are many solvers, efficient solvers for quadratic optimization problems. It's quadratic programming. It's relatively easy to calculate the optimal solution. If there are nonlinearities other than quadratic, what we can do as a data scientist that formulates this task is to have an objective function that is at least twice differentiable. Because in such case, if the task is convex, we can use the sequential quadratic programming algorithm. It's also very efficient algorithm, and in every iteration, this algorithm locally approximates the objective function with quadratic functions and solves the quadratic problem task iteratively. So this is, I hope you catch it, that it is important what kind of a function we will use in our task, right? Like decision trees. They are not differentiable. So because we have this if-else statements, if the value of x1 is higher than something, then the output is this one. So it's not differentiable. We have to avoid some forms of machine learning methods while creating our predictive model, which constitutes the set of constraints, which is a part of a set of constraints. Yeah. So additionally, the objective function should be given in an analytical form, so we can determine derivatives first, and sometimes if it's required, the second derivative. Well, sometimes, for some reasons, the analytical form of the function is unknown, or the function cannot be differentiated. And in such a case, there are other methods that are not based on gradients, such as Powell's method or global optimization heuristics that can be used. So we was talking that the sequential quadratic programming is a really powerful method that we used a lot in our projects, but it requires a convex problem. So what does it mean? What is the solution domain convexity? In some cases, we cannot expect numerical solver to find global solution. So what is this global solution? The best solution in the entire feasible region. We can be sure of that only if the feasible region is convex. Otherwise, we can just say it's a local optimal solution, not the global one. But if this feasible region is convex, then the local solution is also the global solution, the best solution for the whole solution space. So what is convex region? This is not a plan of an airport. As you remember, this is our feasible region. This is our feasible region from the previous task. And the convex region is a region in which any 2 points, like this one and this one, or this one and this one, can be connected with a line, and the entire line remains within the region. In case of a 2D case. This is non-convex solution domain, right? Because we take this point and this point, and not the whole line is within the feasible region. So unfortunately, including second-order constraints or higher might give non-convex solution domains. So we have to be really careful with this. May or may not, because if we will put this constraint this way, it will still be convex task. So we have to keep this in mind while formulating our optimization task. In case of non-convex solutions, non-convex problems, like this one, the result obtained depends on our starting point. If the starting point is here, we will follow the gradient, we will achieve this constraint, and we will end up here, which is a local solution. This is a local optimal solution, but not the global one. The global one is here, and we can achieve it if we start from here. How to deal with this? We can, for instance, use the genetic algorithm. This is a heuristic that help us to solve such problems. And it is quite popular. However, I think sometimes it is too popular. So it's good for simple tasks. It's good for the task where we don't have a big number of variables. But when the problem is big, we have many decision variables, many constraints, it's really hard to use the genetic algorithm. The calculation time is huge, right, in such a case. So it's, like I say, it's good for small tasks. So let's try to see how such method works. We have an initial set of solutions. Those are initial solutions, those red points, and they form a population 0, so the initial population of individuals. each individual, like this dot here, has a genome. The genome consists of just two genes, X1 and X2. And the value of those genes, the mutations of those genes translates into the phenotype. So the phenotype is the way how we look, how many hands do we have, what is the color of the eye. So the phenotype also decides about our adaptation to the environment, how good we are for the current environment. The lion is good if he has sharp teeth and if he's fast, right? The antelope is good if she's careful and have a good healthy eyes, so she can see the lion, right? So in this particular case, how good the individuals are, this is decided by the function, by the function that represents, let's say, the environment, right? So the objective function. If we put this x1 and x2 to the function, we will see some results. Here we would like to maximize this function. This is, let's say, the efficiency of the process. So the better the efficiency is, the better the combination of genes, the better the individual is. So such individuals with higher efficiency, in this particular case, efficiency, maybe the higher production, the higher incomes from production, etc., the higher adaptation, the higher objective function are better, right? So they have a higher chance for reproduction. They are more handsome. In the real world, you have to be handsome and intelligent to find a partner and have kids. Of course, at least you have a better chance to do this. Of course, luckily, if you are less handsome or less intelligent, you still have a chance for reproduction. Maybe it's slightly lower. This is awful. I mean, so behavioral, but that's the way it is, the nature. It's brutal. So now when we know the scores of each individual, it's time for reproduction. It's time for another population. So two individuals can have kids, so they have to find a partner. Of course, the better your score, the better your objective function, the better your adaptation to the environment, the higher is the chance that you will find a partner and have kids and take part in the reproduction process. So this guy over here, he's unlucky. His adaptation is low. The objective function value is low, and that is even more important, he's outside the feasible region. This guy is very handsome, but also this one. So they have a high chance for forming a family, have kids in the next population. So let's see how the life goes. Yep, so as you can see, the guy here have a lot of kids, the guy here, but also this guy. They had a chance to be parents, so they form, let's say, families, they find partners, and now they can exchange genes between each other. So there is a crossover operation like in the real life on your genome. The X1 from this guy, the X1 from this guy can be replaced with the X1 from this guy, or they can be somewhere in the middle, depending on how we define the crossover operation. So in the population number one, we have two groups of two tribes, two groups of solutions. And of course, there is not only the crossover operation, there's also a mutation applied in like in real life. So if the parent has x1 here, the kids can have like, let's say, x1 over here or here. The mutations are possible, and the level of mutation, how big the mutations are, this is a parameter we can change in the algorithm. The better the exploration of the solution space, but the worse the exploitation of the interesting region where the optimal solution can be. Okay, so we have a population of number one. Of course, those individuals have high chance for reproduction, as well as those they can form families. All the combinations are possible. So in the next populations, the kids are mainly here because, well, there was more food, the climate was better here, right? So they have a better adaptation to the environment, those individuals. But still, there's one tough guy who survived in this worse place on this little earth. His teeth was not so sharp. Okay, and of course, those individuals have the highest chance for reproduction. We have another population and another one, and this is the best the algorithm can find. This is the winner. Okay, and but you know, we have to remember that the optimal solution is here. So the algorithm was not able to find the best solution, the optimal solution, but he find a solution that is close to the optimal. So it's, let's say, a suboptimal solution, right? What happens to the guys that were outside the feasible region, like this guy over here? In fact, he's not handsome at all because he's outside the constraints. So he has a small chance for reproduction. Sorry, buddy. All right. So that's the way how the genetic algorithm works. I told you that it is popular, and even too popular, because in my opinion, too many times it is used when the other approach is possible, when the solution is convex, where we can use the linear programming or sequential quadratic programming. So because sometimes where we are lazy and we do not want to identify this function, right? And translate this function into a set of equations that can be used in the optimization task, we'll just apply the genetic algorithm. But remember, it's not scalable. It's not scalable. The calculation time might be very high, and we are not sure if we find the best solution. So it's useful, but you have to be careful with using this algorithm. You have to know when to use it. And talking about this function, the function that tells us how well adapted we are to the environment. This function can be created by someone else. We might not know the form of this function. In this case, we can use the genetic algorithm. For instance, it can be the simulator that tells us that for this particular parameters, the values of these particular parameters, x1 and x2, let's say for this particular temperature and for this particular flow, the heat losses in the district heating network are at the particular level. Right? We don't know how it was calculated. We have the only access to the simulator that sends us the results. Then we can try to use genetic algorithm. But if this problem is bigger, the number of decision variables are higher, we should try somehow simplify this, in this case a simulator, a function not written by us, try to approximate this, try to make a model that can be used in a set of as a set of constraints here, right? This is like here. This is important. Okay, another topic. This is some of the function that I got from another project. So it's artificial, but let us assume this is a function of savings. This is our objective function in a function of oxygen and opening of overfired air dampers, of dampers. So this is a topic related with the combustion process optimizer. This is not the real shape of the savings function, but let us pretend that it looks like this. So we have two peaks. So we should work with low oxygen and high opening of OFA dampers. There is a valley and another peak, also a good solution, but this one is better. And of course, it doesn't look like this in the combustion process. It's nonlinear, but without such valleys. But there are cases when we can see such objective function. So what can we do with this? Can we try to simplify it to make it twice differentiable? If so, then how? Maybe instead of those two peaks, we can approximate it by the Gauss function, who knows, or the sum of Gausses, or other function that is twice differentiable. This part we can treat as a plane. Who knows? Maybe we should use the genetic algorithm. In such a case, we don't have to do nothing with this. If we have a simulator or a function that tells us what is the savings for current value of oxygen and alpha dampers opening, then we can use the genetic algorithm, and that's it. But if the number of decision variables is higher, we should be very careful with this. The constraints are not shown on this figure, but we should remember about them. If we increase the oxygen level too high, it might be hard to get out the gases from the combustion chamber by the induced draft fans, and induced draft fans will hit the maximum load, 100%, and there will be a run bank signal sent to the control system, and the load of the unit will have to be reduced. So if this is the case, and this is the case from the real project that I had, then such a constraint have to be included in the optimization task. Okay, and few words about the mathematical model of optimized mathematical models. The model of a process that we would like to optimize is usually a part of a constraints, right? Usually those are equality constraints. If I change the pressure, I will see the change in the temperature. If I have to find the proper parameter of the pressure, but the temperature cannot be higher than some limit, I need to find a link between my decision variable and this constraint. I have to make a digital twin, a model of a system that covers this relation. It can be a thermodynamic equation, it can be identified based on the data. Based on the data, it can be a mix of those two approaches. If you want to optimize the district heating network operation, then we need to know the relation between supply water temperature and the flow in the network, right? So this is the example. If the real life example that was discussed in the last video, the water temperature, the supply water temperature is the decision variable, but of course if we lower the temperature, the valves in the substations, in the buildings will open because they need more heat, and the flow will increase. So in order to find the optimum value of this temperature without violating the flow limits, because the pipes have some diameter, then I need to know this relation. And in this particular case, we use the machine learning approach to identify it. If you want to optimize pump's operation, we need to know what is the efficiency of a pump in the function of some parameters, like, for example, flow and discharge and the supply pressure and the difference between those pressures. If I want to optimize the combustion process in a power boiler, I need to know what is the relation, for instance, between the oxygen level and the CO emission, because my goal is to limit the CO emission, and of course, if I add more oxygen, I will limit the oxygen emission. But on the other hand, I will increase the NOx emission. And so in order to find this compromise between those two different goals, I need to have the model. In this particular case, in this project, it is identified on the fly based on most recent data. All those relations that I mentioned, expressed by linear or nonlinear equations, forms a set of constraints. Of course, we can have a different constraints as well, like technical limits, like constraints related with some agreements between parties. But the models of a process are at least part of the set of constraints. And of course, if you would like to use the, for instance, SQP method, sequential quadratic programming, we should create this model in a way that it's twice differentiable, right? The decision tree is not a good choice. The artificial neural network, probably you should approximate the network, the solution space, by maybe the quadratic model in particular process operating points. Maybe it's the best choice. Later on, I will show you another frameworks that allow us to use more complicated models, even artificial neural networks. So while modeling a process with the intention to optimize it, we have looked for compromise between complexity and accuracy. We can have a very accurate model, but it could be hard to use it in the optimization procedure. We can have linear equations that express our, that forms our model, but they might be not accurate enough. The solution found using such an optimization procedure might not be possible to apply in reality. The more complex the model is, the more difficult the optimization task becomes, and it takes more time to solve it. Sometimes the convergence issue may appear as well. Increasing model accuracy, and usually the complexity as well, does not always bring better optimization accuracy. Sometimes we may lose solution domain convexity while upgrading our models. This may result in finding local solutions only. So we have to really find a compromise between this complexity and accuracy. Moreover, physical and statistical models, of course we can, or the mixture of them, lose accuracy over time because of devices are getting older, so there's a device wear, the fuel is changing, the number of consumers of heat or gas is changing, so the environment is changing, and our models should adapt to those changes. So I will talk about different adaptation methods. They might be retrained from time to time, or they might be identified on the fly even. So this is the end of the part one. I've discussed different approaches that we are using while solving the optimization problems when we have continuous variables, and this is a typical problem for industrial processes, when you have to find optimal value of parameters. But there are also problems with discrete decision variables, and it will be covered in the next video. In the next video, I will also show you how to formulate, how to code the optimization task in Julia programming language and how to solve it. And also I will talk about dynamic programming, which is a good framework for decomposition of our optimization task and for finding a link between the discrete variables and continuous variables. Thank you for watching and have a good day.